Okay, so this is going to be, kind of situating this in my morning presentation. So this is one particular method that aims at getting external validity using an assumption or allowing for there to be different treatment effects by subgroups across sites. Okay. So I think a lot of this kind of motivating material I can skip. I think Rachel summarized using two different citations the sort of debate on how much we can extrapolate from a given evidence base from RCTs.
We got land. We both got land.
Yeah, that's right. Yeah, okay. And where some people, this is probably a bit dated in the Banerjee, Hay, and Duflo references, but there are certainly people who, or nonetheless, sort of policy recommendations made on the basis of RCTs for a lot of different contexts in practice. And then kind of opposed to that is a nihilistic view which sort of takes it that studies, or the results from a study are only useful in that particular context, which, as Rachel also said, indexes place as well as time. So it's not a very productive use. Again, like the types of questions that we're interested in answering are, determining what, where we can generalize, where we can't, and that's the objective here. Okay, so what I'm going to do here is move away from point identification and provide bounds on the effect of a treatment implemented in a new place on the basis of experimental evidence from somewhere else. All right, so one of the empirical examples is going to be looking at a transfer program which had David Mackenzie and Chris Woodruff, who I'm sure many of you know. So giving transfers to Mexican micro-entrepreneurs in the city of Leon. All right, so they find a large effect on monthly profits on the order of about 40% of the value of the transfer, so a very large return to the value of the transfer. And so the question that I'm going to be asking is, what do the Mackenzie and Woodruff results, what can we learn from the Mackenzie and Woodruff results and data from a national microenterprise survey about the returns to a similar program in other cities in Mexico? Okay, so getting into the setup. So the setup's going to be, so this is, in a sense, not exactly a meta-analysis because we're going to be thinking about largely two sites, so an experimental site and an alternative context. And I'll talk a bit at the end about what this framework would imply about additional experimental sites, how you would use information from additional experimental sites. Okay, in the experiment, we have untreated, we measure untreated outcomes and some characteristics, treated outcomes and characteristics, and the alternative context, what defines it is that either everyone there is treated or everyone is untreated. So for concreteness, we're just, for the purposes of this presentation, I'm going to talk about everybody being untreated. Okay, so the treatment is like an innovation. Okay, so if we were in the case where average effects were supposed to be the same for individuals with the same characteristics, then we only have to do this reweighting exercise in order to estimate the average effect in the alternative context. Okay, but we have seen evidence that even conditional on covariates, average effects differ across contexts. And so the method provides one way of generating robustness to the possibility that treatment effects differ within subgroups across locations. Okay, so sort of re-summarizing the structure. So the idea is that in the experiment, you have the control group, the treated group, and then in the alternative context, you have just a control group. And so the idea is that we have this information. So even when we're looking at a set of individuals who have the same characteristics, who belong to the same subgroup, we have information on them, additional information on them in the same treatment status. So we can see the distributions of the outcome among the control group and in the alternative context. Right? And so differences in those distributions are indicative of differences in unobservables across the contexts for people with the same characteristics. All right, so how can we use that knowledge that the distributions differ and therefore the unobservables differ to map into a prediction for treated outcomes in the alternative context? So the assumption that I'm going to make and go into in more detail is that the conditional distribution of the treated outcome, where we're conditioning on a particular value of the untreated outcome, is consistent with the experimental results in a sense that I'll make precise. So that allows, imposing this assumption allows us to map the differences in these distributions into bounds on the average effect in the alternative context and deliver bounds that are wider when the two subgroups appear to be observationally more different in the sense that their untreated outcome distributions are more different. Okay. So there's a refinement that you can make to the bounds, which is to impose assumption on the degree of dependence between the treated and the untreated outcome. Okay, so often we'll think that there's positive dependence between the treated and untreated outcomes, and we can parameterize how positive we think that they are. So roughly speaking, positive dependence means, in the Mexican micro-entrepreneur example, the people who have higher profits without the transfers are also tend to be the people who have higher profits with the transfers. And so imposing this additional assumption on dependence is going to generate tighter bounds, and it's also going to give us a sensitivity analysis interpretation to the results. So for example, we can say, like, how strong of assumptions do we need to impose in order to draw a specific conclusion, say that the treatment effect is a positive? Yeah, David.
Is there a reason why you're saying dependence rather than correlation?
So I mean, so it's going to be non-parametric dependence. So yeah, so not directly the product moment correlation. Yeah. Okay. Question? Yeah. Okay. So jumping into the empirical results. So the Mackenzie and Woodruff experiment was quite small. It was about, I think it was about 200 micro-entrepreneurs. And in the actual paper, the authors are pretty cautious about interpreting the results. But so the benchmark, so I guess let's say the benchmark frequentist method is overconfident in the extrapolation exercise and actually ends up, for reasons that I'll explain, being more confident in extrapolating, more confident about the treatment effect in all of urban Mexico than it is in sample. Okay, so that's not a very attractive feature of that particular method. Okay, so a second empirical application is looking at two evaluations of the same remedial education program done in two different Indian cities. And here you can use the results from one city to try to predict the results in the other, so very similar to the kind of external validity exercise I was discussing. So here the benchmark method is overly pessimistic and concludes that we don't learn anything about the effect in one place using the results from the other. And then in this case, the bounds are in fact informative and they do contain the observed causal effects. So more details on that. And so I think with this audience, I'm going to focus on, I'll be relatively quick in terms of the general methodology and spend some more time in the empirics. Okay, so the first thing that I'll do is just illustrate a simple example about like what is this consistency with experimental results assumption, and how do the bounds kind of work intuitively. Oh, but I do want to first illustrate the benchmark method. So the benchmark method is, so it's frequentist, it's based on pre-testing. So for the Bayesians in the room, that'll be instantly unpalatable, but there are reasons, even within a frequentist framework, that this is kind of undesirable. Okay, so what do they do? So this is a paper by Joseph Hotz, Julie Mortimer, and Guido Imbens. And so they also have this intuition that the untreated outcome distributions are going to be useful for telling us how the people in the same subgroup but across different contexts differ. I don't know what that was.
Astral projection of Susan and Guido.
Yeah, exactly. Okay. But what they do is they test. So they test whether these distributions are equal. And so if you fail to reject, then you just do the reweighting approach. You accept the assumption that within subgroup across contexts, treatment effects generalize perfectly, and you move on. And if you reject, then you abandon the extrapolation exercise altogether, and you conclude that you don't learn anything from one site using the results in the other. Okay, so for the first one, the test is very often going to be underpowered, and then the second is sort of unattractive implication that we don't learn anything if we reject this test. Okay, and so what I'm doing is quantifying the uncertainty about the generalization that's coming from sampling. So those are going to be the confidence intervals around the bounds, and also from these differences in the outcome distributions. Okay, so literature, many of these things I think have already been discussed, so I'm going to skip that in the interest of time. Okay, so let me get into this little example. All right, so this is going to be a stylized version of this. Oh, yeah, go ahead.
Sorry.
Just to fix, if you could go back to the method slide, just fix the basic idea. So the test is, can we conceptualize it in terms of like a propensity score matching on of observable characteristics across the two control groups, across the two contexts? Is that a bad way of thinking about it?
There may be an implementation of the test that works that way, but so you can think about something very simple, which is, let's say there are no covariates. So you just take, so Leon, Mexico, and you just you would just test the equality of so an implication of the equality of the distributions would be equality of the expectations, and so you would test whether this holds, for example.
That's a specific implementation they suggest. Are they doing full column graphs?
So they actually do a difference in means test, yeah. But yeah, I mean.
Unusually stupid.
Yeah. But yeah, so, you know, to do this properly, you would do like an actual test of equality distributions rather than just means. Yeah. Does that clarify the point?
Yeah. So, but it's always okay, and without even thinking about covariates.
No, so I'm saying, but so you would test, you know, covariate by covariate. So let's say like, you know.
Oh, I think.
Yeah. And you could have a test statistic that aggregates across covariates. Yeah. Thanks. Okay. All right. So, all right. Simple example. So let's start by considering binary outcomes. So let's say that micro-entrepreneurs are either high profit or low profit. And we have some experimental results from the city that I'll refer to as E. And so what happened when we put in the treatment? It went from, the share of high profit entrepreneurs went from 1/3 to 2/3. Okay, so the average treatment effect is 1/3 increase in the share of high profit entrepreneurs. Okay, so now we're faced with this alternative city, call it city A. And there, the baseline distribution across the two groups is that half of the entrepreneurs are low profit, and everybody's untreated, there's no transfers. Okay, and so the way in which to start to think about the method is that the average effect of the transfers in A is going to depend on the share of entrepreneurs who are high profit without transfers, who are also high profit with transfers, and the share of the low profit entrepreneurs in city A, who, when given transfers, are going to become high profit entrepreneurs. Okay, minus the share of high profit entrepreneurs under control, or rather already. Okay, so the experiment will rule out quite a lot of possible distributions, where distribution here is just a pair of these probabilities. Okay, so in principle, without the experiment, you couldn't rule out anything in this unit square. With the experiment, we only have to deal with the distributions that are, in this sense, consistent with the experimental results. So any point on this line is consistent with the experimental results. All right, so how do we then generate bounds? So we basically map these bounds, which you can think of as bounds on the distribution, into bounds on the treatment effect. Right, so if we assume that all of the individuals who had high profits without transfers are also going to have high profits with transfers, that's going to give us the maximum average effect, and that's an increase of 25% in the share of high profit entrepreneurs. Alternatively, if we assume that all the high profit entrepreneurs now realize low profits, then we get the minimum average effect, which is 0. Right? And then intermediate assumptions are going to give us intermediate average effects. So, so the first kind of takeaway from this example is that if we increased the differences in the untreated profit distributions between A and E, we're going to get wider bounds. And in particular, the bounds will include negative values. Right? So if we had 2/3 high profit entrepreneurs at baseline in city A, then the bounds would include negative values, including 1/3. Okay, so now you start to think about what all is allowed by these bounds, and you may, your mind may rebel at the idea that the treatment is so powerful, that giving cash transfers is so powerful, that everybody who's an entrepreneur in city A without the transfers is going to have low profits with the transfers. So it's natural to believe that, you know, there should be positive dependence between your profit realization with and without transfers. Right? If you impose the additional assumptions on dependence, then you're going to get tighter bounds. Okay, so if you assume perfect dependence, then you get just a point estimate. Additionally, if what you want to do is evaluate a particular conclusion, then you can do that. So the conclusion is, will the average treatment effect in A be positive? Well, that's only possible with this minimum dependence, which we thought a priori was implausible. But so one point that I want to make is, so in some sense, your problem is pretty easy if you're willing to assume perfect dependence. Now your point identified, but that may not always be. That's often, in fact, so it's often rejected empirically in the experiments, and in practice, it's also often hard to square with knowledge of the context. So, you know, sometimes when individuals are getting cash transfers, maybe that allows them to get some training and join the labor market, so their profits become zero. So allowing for some slippage away from the perfect dependence benchmark is useful. Okay. All right. So in terms, how much time do I have? Okay. Okay. So we go to 3:40. Okay. All right. So this was a really simple example. There are obviously a lot of complications in real situations. So I didn't have any covariates in the example. Basically, what you would do is just condition on covariate values and rerun the analysis. So non-binary outcomes introduce a lot of the complications, particularly in estimation. So you can get imperfect correlation when people leapfrog each other in the distribution. So the people who were sort of getting the highest profits in under control, they get skipped in the distribution when the cash transfers are given. All right, and so the computation of the bounds is a high-dimensional problem, but if you have discrete or in case of the micro-entrepreneur paper, discretized, then you can set up the computation of the bounds as a linear programming problem, which is easy to solve. Okay, so dealing with the fact that data come from samples, we can bootstrap confidence intervals using methodology from Stoya. And then this I'm not going to talk about too much, but so you could not like the consistency with experimental results assumption. You could think that there's some deviation in the distribution of y1 conditional and y0 across the sites. And you can give that also a sensitivity structure. So in the paper I show you can parameterize that. And so then you have like a two-dimensional sensitivity analysis. Okay. So let me skip most of this. In general, yeah, we have general binary treatment, we have general outcome, covariates, contexts E for experiment, A for alternative. So in the experiment, we have random assignment. In the alternative location, everyone is untreated. And so what we're after, so basically, since everyone is untreated, we can already identify the untreated outcome. what we want to know is the expectation of the treated outcome in the new place. Right? And so if we expand the definition of the treated outcome, what it can be decomposed into two objects that are identified and an object that's unknown. Okay, so we know the distribution of covariates in the alternative location, and we also know the distribution of untreated outcomes conditional on covariates in the alternative location. What we don't know is the distribution of, or the expectation of y1 conditional on a particular value of y0. And in fact, the experiment doesn't point identify this within the experiment either. That's why we get bounds. Okay, but using these distributions from the experiment plus this consistency with experimental results, we can get bounds on this object also. Okay. So again, this is a statement. So the experimental results allow for many joint distributions, which in turn generate many conditional distributions. I'm assuming that the conditional distribution that applies in the alternative location can be generated as one of the possible distributions from the experiment. Okay, and so the analog in the general case, so this is going all the way to the continuous case of perfect dependence, is that the treatment preserves the rank, a person's rank in the distribution. So this is the control outcome distribution, the treated outcome distribution. The treatment maintains your position in the distribution. Right? But the experimental results are also consistent with rank switching. Right? That's going to give you the biggest variance in treatment effects. If the best off people become the worst off people when you give them the treatment. Okay, again, this is a formal definition of the consistency with experimental results. So necessary condition for that is that you have the same, so when the untreated outcome distributions conditional on covariates are the same, then that implies that the expected treated outcome is going to be the same. And it's sufficient if we have that y1 distribution conditional on y0 and x be independent of the site. Okay, but we can relax this condition. Okay, so there's going to be some support conditions. We can only do this on common support of the y0 given x and x. And so this is the formal statement of the bounds. Okay, what do bounds look like when you impose a constraint on dependence? Yep, the perfect positive dependence, it point identifies ATE, but it's not necessarily realistic. And this is usually a case we want to exclude. Right, so the way that I parameterize the dependence is by a normalized version of the Spearman-Rowe measure of nonparametric dependence. And so what we're going to say is that, so the bounds were defined in terms of copula functions. So copula, it maps is a mapping basically between the ranks. So this is one copula, this is another copula, but keeping the marginal distributions fixed. Right, so here we're allowing for any copula, so that means we allow for this perfect dependence copula as well as the rank switching copula. And so, this row is a characteristic of the copula, and so we can then implement the constrained dependence bounds by restricting the space of copulas to have this measure of dependence be at least equal to rho L. Right? And then we get some bounds on the average treatment effect. Okay, so I mentioned this issue about computation with basically more complex covariates than, complex outcomes than binary. So the nice thing is that that this optimization with discrete outcomes and covariates is actually a variant of well-studied optimal transportation problem, and which can be solved by linear programming. Yeah.
Is that Is that the mathematician Villani?
Yes.
Okay, I am delighted to see his. I forgot that.
If only I had a picture of him.
I know, exactly.
To delight you even more. He's a member of French Parliament, and has these huge bow ties. He's also a mathematician, and he writes comic books. He's an amazing character. Okay, and so then I can do, once that mapping has been made, I can do this linear programming representation and estimate using sample analogs. Okay, so here we're going to have discrete outcomes and covariates. All right, so inference I'm not going to talk too much about. And just this is describing the Bootstrap procedure that we use to generate confidence intervals around the bounds. Okay, let me get into the empirics. All right, so in the empirics, I'm going to be contrasting the results with the Hot-Simmons and Mortimer procedure. So remember how that worked. And I'm going to be looking at the transfers to Mexican microenterprises. In this case, that procedure is overconfident. In the two experiments in India, it's going to be overly conservative. Okay, so digging in a little bit more on this Mexican microenterprise example. So this was 2006 in the city of Leon. We're going to be looking at a discretized measure of monthly profits. The treatment was a fairly large transfer. So 50% of the treated group got their transfer in kind, but they didn't, there was, in the original study, they didn't find differential results across these two types, so I'm going to pool them together. And so you get this big average effect in Leon. So monthly profits increased by about 600 pesos. But it was a really small experiment, so 207 entrepreneurs, and so their characteristics are, so this is already a pretty selected sample, so I'm not going to use any covariates in this case. Right, so they were 22 to 55, working in retail, small capital stock, no paid employees, basically full-time in the microenterprise. Okay, so nice thing about this experiment is that the questionnaire is the same pretty much as the National Microenterprise Survey. So we don't get into too many issues about variables being measured in different ways. And so the question I'm going to be asking is, what does the experiment tell us about the returns to cash transfers in the cities represented by the National Microenterprise Survey? Right, so when I impose these characteristics, I get a sample of 907 entrepreneurs. Okay, so what do the untreated outcome profit distributions look like? So again, this is discretized. They are, so not tremendously, but substantially different. Okay, so the distribution indexed by the X's, that's the experimental control group, and the microenterprise survey is the straight line. So you see more zero profit observations in the microenterprise survey, but other than that, they're fairly similar.
Is zero the only point where you, like, a frequentist test is going to reject
Equality? So I actually do apply the Kolmogorov-Smirnov, and you can't reject. Yeah. Okay, so in the Hot-Simmons and Mortimer world, so I mentioned that we are more confident in the prediction for all of Mexico than we were about the experimental treatment effect. Well, that's because we have 907 entrepreneurs with which we can estimate the untreated outcome mean. Okay, so we have good information about the untreated outcome mean. All we need to do is to get the treated outcome mean, and it turns out that the confidence interval is shorter for the average treatment effect. All right, so what do you do when you impose bounds? Okay, so this is the dependence parameter, rho L. So if we impose perfect dependence, we get a point, and then the gray here are the confidence intervals. So as you move away from the perfect dependence benchmark, the bounds get wider, but actually over this range, they never include 0. So the set estimate never includes 0, but you can never reject a 0 effect. All right, so if you want to interpret the set estimate, you would say something like the representativeness that we saw in these untreated outcome distributions, maybe that's promising in terms of the generalizability, but the sample's really small, so we should be really cautious about it. Okay, so getting into these two remedial education experiments. So this is a well-known experiment. It was in remedial education. So the researchers assigned a remedial education teacher to a student's class. That was the treatment indicator, and that teacher worked with 15 or 20 students for about half the school day. All right, 2 experiments over 3 years, one in Mumbai and one in Vadodara. So I do this exercise of trying to predict the results from one using the other. All right, so I'm going to be looking at math proficiency. Downside, so here we do have some measurement issues. The measurement issue is that the researchers administered different math tests. And so I use, for the outcome of interest, the student's maximum grade level competency in math. So this turns out to be something that you can get sort of throughout the former, I guess it's still called the Commonwealth, right? You can get that throughout the Commonwealth. So not only useful in this case, but perhaps useful in others. Okay, so I have to limit myself a bit because year 2 in Mumbai had compliance problems. I want to abstract from that. And so what we have for Mumbai is year 1, which is 3rd graders, and then Vadodara, we can use both years. Okay, so we don't actually have a lot of covariates that are measured in the same way, again. What is the most powerful covariate that's identified in the original study is the maximum grade level competency on entering 3rd grade, and then the outcome that we're going to be looking at is the maximum grade level competency on exiting 3rd grade. Right, so I'll operate conditioning on the competency. And so what you see from these graphs are that so these are both of the control groups, conditioning on the competency on entry. So the distributions are pretty different. And in fact, we reject their equality for each of the cells. All right, and the Hot-Simmons and Mortimer, we would say, don't do any extrapolation. But what turns out to be the case if you apply the bounds. So these differences mean relative to the Mexican example. So again, point estimate at perfect dependence. But the bounds expand pretty quickly as you move away from perfect dependence, and that's because of these differences in the untreated outcome distributions relative to the Mexican example. But what we see, so if we give it this sensitivity analysis interpretation, so what we can do is reject a 0 average treatment effect so long as dependence exceeds 0.937 of the maximum. And that sounds pretty like a pretty large amount of dependence, but it's not necessarily implausible for outcomes like your rank in a distribution of something that's derived from a test score. Okay, so you don't get. This is saying there's a limit on how much leapfrogging goes on. Most of the treatment effects are increase of 1 in grade level competency. that's going to be implied by this result. All right, and so under these, under this assumption on dependence, we actually do have the bounds encompassing the observed treatment effect, for what that's worth. Okay, so let me wrap up here. So this is a specific way of quantifying the uncertainty. We've talked about many ways of quantifying uncertainty. This is one, associated with doing the generalization exercise from one randomized experiment to a specific target. So in this framework, if you wanted to start to include multiple experimental sites, what you would do is to intersect the bounds. So that would be the way in which, I mean, that's the way that aggregation works in partial identification. Yeah, so you would basically get a set of these bounds from each experimental site, and you would intersect those bounds to get your prediction, your final bounds. Okay. And so this particular quantification is how strong of assumptions do we have to draw in order to come to a specific conclusion about the treatment effect in the experimental site. Right? So I think like a last point is that many of you may be familiar with this Imbens and Wooldridge review article on treatment effect estimation. And so what they claim, and I've heard this in other places, is that you never really care about the joint distribution of the potential outcomes. Like, all that you care about if you're, you have a standard social welfare function is the two marginal distributions. But in this exercise of transporting treatment effects across contexts, this shows that, in fact, that's not the case. So this is the case, potentially the case, given a particular social welfare function within a context, but not necessarily when transporting across contexts. Okay. Thanks very much.